Howdy, it's your local sugar lump creature. I feel like wearing a hat today, because it feels like I copy-paste my drawings from another episode, you know? But also, I thought I should make this small change in this episode for the sake of variety. Other than finding a new style, we will be finding the pseudo-foci of this parametric curve called the trochoid. What's a trochoid? Well, a trochoid is a graphical representation of my depression throughout every passing hour of every day. It can vary so much that I sometimes feel twice of it constantly in the hourly cycle. But in geometrical terms, a trochoid is the motion of a rolling circle traced by some line that pedals from the circle center. This pedaling line is usually the radius. Nonetheless, the trochoid's parameter is expressed as at minus b sine t, comma a minus b cosine t, where a is the circle's radius and b is the pedaling line length. Based on this parameter, the shape or pattern of a trochoid varies upon the inequality of these two variables. Like, if the pedaling line is the radius or if b equals a, the trajectory will be a continuously repeating arc called a cycloid. If the pedaling line is longer than the radius, or if b is greater than a, the trajectory will be a prolate trochoid, or a loop-to-loop as I call it. And if the pedaling line is shorter than the radius, or if b is less than a, the trajectory will be a curtate trochoid, also known as a boring excuse of a sine wave. This variance of a trochoid will become important in pinpointing the pseudo-foci, so just be aware of the three types. Now that you're familiar with the three patterns of a trochoid, let us now shift to the concepts of calculus and algebra to locate the pseudo-foci of a trochoid. Like before, achieving this requires the three-step rule to directly pinpoint them. And just in case you forget, the 3SR is a method in which we first differentiate the x component and the y component 3 painful times. Then, we arrange all those derivatives in a specific, disorienting configuration of an equation, which we agonizingly poke to a simpler one and juice out its solutions. And then, we take another headache-inducing configuration where we plug each of the solutions to every single damning term. I feel infuriated about this because before I even began producing this video, I went through number hell doing the method to the trochoid parameter, and it took me a handful of long, painful attempts, but I finally did it. But because of my miserable rambling, I decided I should keep this video's algebra content to a minimum and get straight to the pseudo-focus. So let's get this started already. Step 1. Differentiate the x component, at minus b sine t, and the y component, a minus b cosine t, 3 times. But first, I will start by writing cosine t as c and sine t as s to shorten the expressions and make them look more organized and less overwhelming. So as a result, this turns the components into at minus bs and a minus bc. With these shorthand components, we differentiate those components 3 times, where the derivatives are as follows: a minus bc, bs, and bc for the x component, and bs, bc, and negative bs for the y component. And that's basically it for step 1. Now for step 2. Solve for t in this long equation that I don't have time to pronounce. This is the step where we change all these prime terms with what we have. When we do, it will look like this. Keep in mind that this is just the shorthand form of the entire equation, where the entire trig functions are not written out. But hey, this equation can be simplified and reduced algebraically, where it would take us like 5 minutes of needless time. Because I promised to say no to algebra this time, I will simply display a time lapse of the equation solving part. So here it is. Eventually, you'll end up with the solutions of pi n and inverse cosine of 2b squared minus a squared all over ab, plus minus 2 pi n, where n is basically any integer. And that wraps up step 2. Let us now proceed to step 3. This is a step with a parameter that represents the evolute of a curve. And to specify that we want the trochoid's evolute, we need to replace every prime term to each of the components and primes of the trochoid parameter. Long story short, replacing every prime will get us to the parametric expression of at minus bs, comma a minus bc, plus a squared minus 2abc plus b squared all over abc minus b squared times negative bs, comma a minus bc. What follows after this part of step 3 is the greatest brain smoothing algebra of all time. This is where we plug each painful solution we had in step 2 to that one t in the parameter and every c and s of the whole thing, which also have a t. Just so you know, we have to plug this long solution inside sine and cosine, and upon doing so, it will give us expressions like this. And each of these are plugged to the parameter, yielding a coordinate of the pseudofocus. But that's not even close to over, because we have to do that again with the other 2 solutions from step 2. But after all the trouble of evaluating cosine and sine and simplifying the parameters, we will end up with a pseudofoci of a times pi plus 2 pi n, comma, negative a over b times a plus b, 2a pi n, comma, a over b times a minus b, and, get ready for this, 2a pi n plus minus a times inverse cosine of 2b squared minus a squared over ab, plus minus 2 over a times the square root of negative a squared minus 4b squared times a squared minus b squared, comma, 4 over a times b squared minus a squared. Again, these coordinates here are the pseudofoci of a general trochoid, which brings step 3 to an end. Let's check out these pseudofoci, shall we? Remember that the existence of the pseudofoci depends on the cases of b equals a, b greater than a, or b less than a, so we'll have to distinguish the pf's of each case. In the case of the cycloid, or b equals a, the only pseudofoci that reside upon the curve are the blue points under each arc and under each low cusp, perhaps. Then in the case of a prolate trochoid, or b is greater than a, the pseudofoci are the same blue points, except one point in each cycle lies inside the loop. However, in the case of a Curtate trochoid, or b is less than a, there exist these 2 extra green points that triangulate with the blue point. This actually reminds me of the secant curve, where 3 pseudofoci reside under each mound because they are flat enough to count as 3 curves over each pf. This is exactly what's happening in the case of the Curtate trochoid, a pseudofocus trio. However, in behalf of all these cases, how do I know that these are indeed the right pseudofoci of the trochoid? Well, this is where we draw an osculating circle where its radius starts from the evolute to the point on the trochoid it corresponds to. As this osculating circle skates along those 2 things, the radius reaches a max length or a min length when its center is on the pseudofocus. Additionally, when the osculating circle passes through these points, the circle either shifts from growing to shrinking or shrinking to growing. With that said, here's a visualization for the other cases. And there we go. We have confirmed that these are indeed the pseudofoci of a trochoid. there are still a couple of things I want to share about the Trochoid, and one of those things is its evolute. Specifically, the evolute of the cycloid, which actually turns out to be another cycloid. And due to this, the center of its oscillating circle moves the same direction the cycloid is drawn. This is one reason why I had a desire to showcase the Trochoid, because the evolute of that certain Trochoid case is congruent to its original curve, which is cool in its own regard. But aside from the unique evolute of a cycloid, I also want to showcase the normal map of a Trochoid. Remember those guys? Yeah. Normal maps, if you forget, are a collection of normal lines that are drawn compactly across the curve. Drawing a normal map with a high line density will start to outline the evolute of that curve. So to properly end this video, how about I show you the normal map of each Trochoid case, huh? Here we go. And that does it for this episode. It's quite a decent length for a PF video, not too long without the algebra part. However, I have some sense of discomfort about removing the algebra parts because it has always been how most of my PF videos are structured. So here I ask about your thoughts on this. Should I straight up get rid of algebra parts or keep them? Or maybe some degree in between? Please let me know in the comments, and I shall consider. Other than that, if for some reason, in some part in this video, your brain process was too slow, then I recommend that you check my description out in the Dismos link below. Wait, no, I had it the other way around. But in the Dismos activity, I write down the algebraic process of each step, especially in step 3, where it's quite a big mess. Other than that, there are visuals that may help your understanding with these PFs, as well as visuals that I used in this video. But to conclude, thank you for mentally surviving up till now in this video. And because of that, I tip my hat for you. Bye bye.